Hello, can you
Good
hear me?
morning.
Okay, morning. Okay. Yeah. Hopefully you have a nice weekend. Uh, yeah. Um. So I think everyone has submitted the assignment 3, right? Okay. So I think today we're going to continue the lecture for the network layer, right? Let's start the slides. Okay. Give me 1 second. Okay, good. I see someone here replied that. Very good. Okay, so yeah, you should be able to see my screen, right? Um, Give me 1 second. Okay, good. So I think last week, right, we ended up at switching fabrics. We were talking about the um, input and output ports, right? And we have the different switching fabrics, right? As a memory, bus, and the interconnection network. So I think we slightly mentioned about the disadvantages of using the memory and the bus, right? But generally speaking, their performance would be their rate, right? Speed, rate, performance would be limited by the bandwidth, no matter the memory bandwidth or the bus bandwidth, right? So how should we do? Do we have any better idea or solution here? Okay, so here is the animation. Just try to record that. Okay, so if there is a datagram passed from input port and to the memory, and memory will pass that to the output port. Okay, similar to the bus. Okay, and I think the more or better idea is that can we use a interconnection network, right? So, for example, the crossbar, the closed networks, other interconnection nets initially developed to connect processors in the multiprocessor. Okay, the general idea is that we want to do that in parallel. Okay, we want to have a multi-stage switch with multiprocessors right here that can help us do the switching thing in parallel. Okay, the idea is that we, for example, here we have a 3x3 crossbar. We have the n times n switch from multi-stages of smaller switches, right? So generally speaking, that we decompose the switch into multiple small pieces, right? And the multiple pieces can doing the transition things simultaneously, right? So for example, the here is a 8x8 multi-stage switch built from smaller size switches. Okay, so if we are using this kind of technique, we can deliver the a mechanism with a high parallelism, right? So the idea is that we divide the datagram into fixed length cells on entry, right? We just divide the data or trunk the data, right? Block the data, right? And then the switch cells through the fabric reassemble the datagram at the exit. The idea just truncate, right? Divide and send to the multiple smaller switches, and they can process at the same time at the end. So here's the animation. At the end or exit, the datagrams will be reassembled together. Okay, so um, this is a general idea, but I think also relate to the parallel processing, right? So because the multiple switches can help you to process the datagrams at the same time, right, in parallel. So that will give you better or higher throughput, okay, or the performance. So the continue switching through the interconnection network. So using these multiple switching planes in parallel can also scale. So here we are talking about two different parallelization here, okay, a parallelism here. So one is different fabric planes, okay. One is what we mentioned that we have the multi-stage switch, right? Here is the multi-planes, okay, multi-switching planes. So for each plane, you can see here the Cisco CRS router. So basic unit is the 8 switching planes. And in each plane, there are 3-stage interconnection network. So you can think about previous slide. So here is the 8 times 8 small multi-stage switch, and we have a multiple fabric plane here. So you can see a lot of parallelism here, right? So similar to the multi-core CPUs, right? So if you have any idea about your CPU, or if you have choose some parallel computing class, we can do multi-nodes, right? And during the meantime, within each computing node, you have a multi-cores, right? So like you have multiple servers there, right? You can process the data like a data center, like cloud, right? Google Cloud or AWS, you can have a you can have an instance with multiple nodes, right? Within each node, there are multi-cores or CPU cores or GPU cores, right? So they can process all the data simultaneously. Here is the same principle, right? You have the multiple fabric planes, and within each plane, you have the several parallel pipelines, right? It's like a pipeline, but multi-stage, same idea. So for this router, Cisco CRS router, it can be up to 100 terabits per second switching capacity, right? It's very high surprising throughput, okay? So, but the key idea is try to leverage the different parallelisms within the router, okay? So that's a general idea about the switching connection, right? And then the next question is that we mentioned that there is a queue from the input port to output port, right? There is a buffer. So there is some similar idea we mentioned before. So in the computer network class, we always mention the queue, the buffer, those things because it can help you to manage the different data unit arriving, right, and to be sent. Okay, so so let's see here the input port queuing. So if switch fabric slower than the input ports combined, so there will need a queue there, right, to happen at the input queues. So you need to manage the datagrams arriving from the input port and to be sent to the output port, right? So the queuing delay and the loss due to the input buffer overflow. So that means that if you buffer in the input port, there is no, as we always mention that. So if there is no buffer, no space there, some packet will be lost, right? So here we just re-emphasize something specifically related to the network layer. So for example, here we have the head of the line HOL blocking. So it means the queued datagram at front of a queue prevents other in queue from moving forward. I think this is straightforward, right? It's straightforward and obvious. So if the something in the front of queue will block the other datagrams in the queue, right? So you can see the left hand side. I should use a laser point. You can see in the left-hand side, the output port connection. So only a red datagram can be transferred. Lower red packet is blocked. So every time there is only one one datagram from the same category can be sent to the output queue, right? For example, we have the three blue, uh, blue, red, and green, right? We have output queues here. So each time there is only one color of the packet can be sent. Packet in the same color can be sent to the output queues here, right? Sorry, output port here. Okay, and here the right hand side is the one packet time later means green packet experience HOL blocking because in the same import queue that red datagram is before the green one, right? So it has blocked the the green one. Okay, so this is some straightforward idea here. And for the output port queue, so he from beginning from last slide, we know that input port queuing, right, is waiting to send the datagram from the input port to the output port. After the output port get the datagrams, it also needs a queue, right? Because you always need to expect that if the data arriving too fast, then the data can be sent out, right? Here is a from the datagram buffer to the link layer to the physical layer and send out, right? Here is the procedure. So there must be a queue here, a buffer, right? To queue the data arrived in the output port. So the buffering required when the datagrams arrive from Fabric faster than the link transmission rate. The drop policy, what is the drop policy? Which datagram to drop if no free buffers, right? So here is some policy or management we understand here, right? So for the next several slides, we will talk about the queuing policy, the buffering management here, right? But the general idea, I think, always the same, right? We have something arriving too fast or faster than the something you can consume that, right? So there will need to be queue, need to be buffer, right? If the buffer is full, how to drop that? If the queue is there, how what is the priority, right? How to prioritize some things in the queue. So there is always some idea here. In the future, if no matter in which kind of the computer system, memory, networking, processor, there is always a queue buffer or something. But these are common things you need to think about, right? How to manage the queue, what's the priority in the queue, and how you can manage the buffer. If buffer is full, how to drop that, right? This is some basic question like when you get some general things, you always need to ask these questions. So the datagrams can be lost due to congestion, lack of buffers, right? The scheduling disciplines choose among the queue datagram for transmission. The scheduling disciplines is that the priority things, right? How you can schedule that. And buffer is how you manage the drop or lost, right? So we will talk about these two things in the next slide. But as I mentioned, this is a really important slide because it's not only in the computer networks, but in other computer system class, you may also encounter this question, right? How to manage a buffer, how to manage the queue, right? How to schedule, right? This is general questions. Okay, so let's see for the output port queuing. Okay, so as we mentioned that the buffering. Why there is a buffering? Because when the arrival rate through the switch exists the output line rate speed, right? So the arrival rate through the speech, for example, you have a very fast speech, but your output link such as the Ethernet, or maybe you are not using the Ethernet, right? You're just using the wireless right connection. Then the output line speed would be could be slower than the arriving rate, right? So then there would be a queuing there, right? Action for queuing there, and it will encounter some delay, right? And also some loss if the output buffer is overflow or is full, right? And how we should design the buffer? That's the question. How much do we need for the buffer, right? So here is some empirical study or experience here. Um, I don't think we need to dig out for the reason why they summarize this formula. But general speaking, you can conclude something. I mean, at least you need to know which parameter increase and you need to increase or decrease the buffer, right? So for example, here, according to the recommend for Commons 3439 rule of thumb, average buffering equal to typical RTT, right? Round trip time, saying 250 millisecond times link capacity. So for example, C is equal to 10 gigabits per second. The link is a 2.5 gigabits buffer. Okay, sorry. So if the C is the 10 gigabits per second, you can calculate the the buffer size, right? You can calculate the buffer size, the 2.5 gigabits buffer. So most recent recommendation is follow this formula, right? ITT times C divided by square n. So anyway, I think this formula definitely many people are researching for this topic. We don't expect to understand how they got this formula, but generally speaking, you should understand the basic principle. For example, if the link capacity increase, do you need to increase the buffer, right? If the RTT time increase, do you need to increase or reduce the buffer, right? If n is the n flows, right? If number of the flows increase, do you need to increase or decrease the flow? Sorry, increase or decrease the buffer size, right? So I think this is a general question you should understand. I think for RTT time, definitely it's if it's larger, right? You need to have a larger buffer because that means the packet could be sent and receive longer and longer, right? You need to have a larger and larger buffer, right? That's makes sense. And if n flows, right? So if you have n flows, right? That means you each flow can um, share smaller buffers, right? So you can reduce the buffer here. And a similar thing for the link capacity. If the link capacity arriving rate is higher, right, you need to increase the buffer. Some idea here, right? You need to understand what is the change trend. But we don't expect to derive the square and y square, not cubic and right, not something else, but right, the general trend, increase or decrease, this idea you should get. Okay. Um. Okay. So not next, I think is just a quick summary. If there is too much buffering, it would increase the delays, right? Particularly in home routers, there is too much buffer. Yeah, I think the buffer is large. The queue time is you have much more delay time, right? And the long RTT, as I mentioned, if the poor performance for real-time applications, it will, sluggish the TCP response, right? And if we recall the delay-based congestion control, the key bottleneck link just a full enough busy, but no full. Some idea here. Um, okay, but the general idea is that the buffer is how we define the buffer is related to the RTT time, right? The network performance and the link capacity, right? The rate, right? And also the number of the flows, right? If you have larger flows, you will need a less buffer. Okay, so that's the idea about how much buffer we need. And then next topic is how we manage the buffer, right? If we have a buffer, if there is some datagrams in the buffer, how we manage that buffer, right? And next question is how we schedule the different flows, right? This is the first for the buffer management. So the abstraction is that we have a queue here, right? So the buffering, there is a queue in buffer, right? Waiting area. If the packet arrives, so for the network or network layer, so there's a datagrams arrive, right? And they are waiting in the queue and waiting to be sent through the link to the other server, right? And the buffer management is which packet to add, drop when buffers are full, right? It can be based on the tail drop. So drop arriving packet if it's a full, right? Or it can be dropped based on the priority. Drop or remove the based on the priority basis, right? So for example, you have if your mailbox is full, right? How should you deal with that? Let's assume that you cannot take all the letters at the same time, right? Every time maybe you can every day you can just take a one or two letters, but every day you could get a one, two, three something letters, right? How if your mailbox is full, how you deal with that? you can just drop everything. If it's full, you can drop out everything arriving, right? You don't receive any new mail if your mailbox full. But another policy that you drop something not important, right? You just take out something important, and if it's full, you just drop something not important, right? Based on the priority. So how can we define the priority, right? That's some other topic. But for the buffering management, these are two policies here. So we can mark the which packet to signal congestion. We can have some different mark, right? So here's the idea. And next idea is package scheduling, right? So I think the buffer management is the general idea is clear, right? How to drop the packet and how to make the priority. But sorry, I mean the general idea is clear based on the priority, but how to make a priority, right? That's something we will discuss later. Yeah, I think maybe you will have a question, which package, which datagram is important, which one is not, right? So that may be, if you remember, we discussed before, that be maybe based on the application requirement. Some application try to mark some packet or datagrams as important or the high priority, right? That's something related to application, but we will mention that later. Okay. So another thing is packet scheduling here. Okay. So the packet scheduling is deciding which packet to send next on the link, right? As we mentioned, if we have the uh, different flows, right? And the buffer, there is only one buffer, right? And you have different flows, how we can uh, measure, how we can manage which packet or which datagram should be sent first, which one should be sent later, right? I think this scheduling is not only be applied in is applied in the network situation. I believe you hear about this in different places, right? So even in your real life, right? So first come, first reserve, right? Like you go to a restaurant, you first come, first reserve, right? And the round robin, I will mention that round robin is a very famous scheduling policy in a lot of places, right? In, for example, CPU or GPU, they have a task, how they can make all the different cores, right? Different processors have the same kind of the amount of the workloads, right? Round robin can help them to balance that. But whatever, I will explain them one by one. So today I may be a little bit quicker than before because I want to uh, uh, quickly mention about this and go to the IP subsection because IP is a key part of the network layer. Okay, so if I'm a little bit quicker than before and you have any question, you just send in the chat. Okay, chat, and I will answer. Anyway, I think here is the packet scheduling. We have the different policy as I mentioned. If the datagram arriving, different flows, different categories, how should we schedule that, right? We have different scheduling policy, first come, first reserve, priority, round robin, weighted fair queuing, what are they, right? So for the round robin, sorry, for the first come, first reserve, I think this is obvious, right? The packets are transmitted in order of the arrival to output port, right? Just which packet arriving, which datagrams arriving first, just send out first, right? It's known as FIFO, right? FIFO, I think in computer architecture is a very famous policy, right? So for the different tasks, or I mean, in the pipeline of the computer architecture. Some of you may still remember that. Okay, so the real world example, as I mentioned, in your when you go to a restaurant, right? First come, first reserve. Okay, and the priority scheduling for this policy, I think it's also as I mentioned, it could be depends on the application, right? But let's just forget how we make a priority. Let's assume there is some traffic has been already classified for high priority or low priority. right? And when the packet and when the datagrams arrive, it can be queued by different classes, right? High priority class and the lower priority class. Okay, here we mark the high priority class in red and the low priority class in green, right, in the figure. And any header fields can be used for classification. And here is the animation. So if there are some continuous packet arriving, some high priority, some are lower priority, we should do the FIFO or FCFS, right? First come, first reserve, right? So for that policy within each queue. But between the two queues, we always put the high priority queue as a first priority, right? We first take off the high priority queue, but within high priority queue, it's a FIFO or FCFS, right? And after we have nothing in the high priority queue, then we use the FCFS policy for the low priority queue. Okay, so send the packet from highest priority queue that has buffer packet and FCFS within priority class. Okay, so let's see an animation here. If we first, there is a packet one arriving, right? And it's in the high priority queue, right? And then the 2 and 3 arriving as later. And now we have the 3 packets, 1 and 3 in the high priority queue and 2 in the low priority queue, right? If we want to send, we first send 1, right? And then we send 3, and then we send 2, right? I think this is obvious. And after that, 4 arrive, and you send 4, and 5 arrive, you send 5, because 4 and 5 is not overlapped, right? And 1, 2, 3 are overlapped. 1, 2, 3 send arrived before sent off 1, right? So is this clear? I think it's not difficult, right? So 1, 2, 3 arriving almost at the same time before the sending out the first packet. And based on the priority queue, 1 and 3 should be first sent out, right? After sent out 1 and 3, you take care of the 2, right? And then you go to the next packet, 4 and 5, right? Yeah. It's like a VIP queue, right? So if some VIP waiting there, they should be always be treated first after that, and then handle the next queue. And if there is some VIP coming later, you just take them again, and then you go back to the normal queue, right? It's like this way. It's working like this way. Okay, and for the round robin, I think the round robin is just a circled idea. It's you just take care of the each classifier or classified queue by class. Okay, you just do a circle, right? And several circularly, right? So you just do a round, and each time you handle classification 1, class 1, class 2, class 3, right? And for each queue, just scan the class queues and sending one complete packet from each class in turn, right? This is a uh, kind of classic. Okay, why I mentioned that for the workload balancing problem, if some of you have idea about how we make workload, let's see. Okay, so red, green, and the purple are 3 processors, CPUs. Let's think about some parallel or concurrent computing, right? So you have 3 processors. You have a lot of incoming tasks, right? And for some tasks, if it's heavy, right, you put it into the red. If it's very light, you put it into green. If it's not very heavy, not very light, you just put into purple. Okay. And if we are doing the round robin, okay, I also have 3 processors. How should you allocate the different tasks into the different processor? Because you want to different processors have the same amount of the workloads, right? You don't want to one have a very, very heavy workload, the one have very, very light. Then there's no balance, right? Overall time would be high. How you do that? How you allocate the different work jobs or workloads into different processors, right? Is that the same as a round robin? So I want to do a pause. Anyone um, understand this question? So if I have the different kind of the um, workloads, right, queue, and I have different processors, right? Should I use the round robin to make sure that each queue or each processor will have a same amount of the workloads? Anyone have the heard about that for the workload balancing in other class? No one hear about that before? Okay, I think uh, if no one here before, okay, although this is not very relevant to the computer network class, but I think if you are senior students and computer system, if you learn something idea about multi-cores, I guess some of you know the multi-cores, right? Or multi-core or parallel programming. So do anyone learn the class for parallel programming? If yes, could you please let me know in chat?
I'm doing it right now.
Oh, you are taking that now, right? Sorry. Maybe my volume is a little bit lower. So who just speak that? Yes, I'm talking about the parallel programming, parallel computing. So you should have a, yeah, in class we have the, yes, something like this, yeah. Okay, yeah, you are learning that this semester. That's good. Yeah. So let me try to add something. If I think the Professor Nance is teaching that, right? So let me try to add something if you are not about to learn that. So for the different processors, let's say if you have a CPU, right? The CPU have eight cores, right? Everyone knows that when you purchase a computer, you must pay attention to how many cores you have, right? Because more cores means higher computing power, right? And each core can take care of some task for you. Is that right? I can use a different core to process different tasks. Is that a basic idea for parallel computing, right? You don't want to, yes, it's like a multi-threading, right? Each thread running in a core, right? Multi-threading is a programming or operating system concept. From the physical layer, there are multiple cores there, right? Each thread could be running in each core, right? So you have 8 cores, you can launch 8 threads. But anyway, you can launch 32 threads. That means many threads running in one core. But let's say 8 cores, 8 threads, right? Each core has a one thread. That means one operating system will allocate some task within this thread to a core, right? You have a lot of cores, not maybe not of, but let's say 8 cores, right? That means you have 8 threads. You can deal with some computation tasks during the meantime, simultaneously, right? And then the idea is that how you can make sure all the different cores have some similar amount of works, right? So for example, we have 8 people moving the stuff from library to classroom, right? You don't want to have Tom to take 50% of the works, and the remaining 7 people take the other 50% of the stuff, right? Because then the Tom will just spend a lot of time, and the other core need to be waiting there, right? They're just chatting there, they're just be idle there, right? And until Tom finishes, the overall time would be very long. Is that correct? You want to have each core to have some similar amount of works. That's my point. That's called workload balancing, right? You want to balance the different cores with the same, not same, but almost the same or similar amount of the workloads, right? Workloads is the computation tasks, right? Then the overall time would be not so long. That's the idea, right? That's an idea not easy to understand, right? Is that right? Okay, so similar idea is here, right? So for the different packets arriving, you want to scan the different queues, right? You want to maintain the queue with the same amount of the packets. You don't want to have a one queue very full, one queue very, less, right? So then round robin is a good schedule policy, right? To go through all the lines, all the queues, each time one by one, right? And as I mentioned, for example, the red is could be um, the queue with a heavy workload. You just allocate the heavy workload to the different processor, right? Do the cyclist thing, okay? Anyway, I say a little bit more things than the computer networks architecture, but I want to let you know this is something you may see in different classes, and at that time you may realize, okay, so this is a good thing we learn in the computer networks. Okay, and another scheduling policy is about the weighted fair queuing. So what is the weighted fair queuing? So that means the generalized round robin based on the weight, right? So as I mentioned, so each queue can have the different heaviness or lightness, right? Some queue are very full, some queue are very empty, right? So you need to, based on the different heaviness of the queue, right? And give the different queue weight, right? So the weight could be based on how the number of the packets in this queue, right? And the calculate its weight, right? It's just a weight divided by the overall number of the packets maybe, right? And then you can based on this weight to do the schedule, right? Which weight is higher, and you give this weight higher priority, right? For example, red queue, if you calculate the W1 is twice as a W2, then you just schedule, you just send out the 2 packets from red queues, right? And then send one from W2, and maybe send 1.5 packets. Let's assume there is a 1.5, but actually no. Okay, let's say maybe 4 for the first one, 2 for the second one, and 3 for the last one. Okay, you can based on the weights to do the schedule. Okay. So these are the 2 scheduling policies for the queues. Okay, and this can guarantee the minimum bandwidth, okay, per traffic class. Is that clear? For the router part, I finished this subsection. Any question before that? Before we go to the IP? IP subsection. Okay, we still have 10 minutes. If not, let's quickly start with the IP datagram format. I think that should be fine for today. So every layer, still remember the HTTP layer, we have the HTTP format. And for the TCP layer, for the transport layer, for example, for the TCP, we have the TCP template, right? And the same idea is that we should have something for the network layer, right? So that's why we need to talk about the IP. So this is the network layer. I think you see this a lot of times, right? Between the transport layer, TCP, UDP, and the link layer. And there is some path selection algorithm for routing, right? For the routing algorithm, right? Forwarding is for per node per router, and for the routing algorithm is a path selection algorithm, right? And we have the IP protocol, we have ICMP protocol. We will mention that. Okay, so I think today, not today, but for this chapter, the most important part is the IP, right? So before you learn some class for the computer networks, you definitely know TCP/IP, right? TCP/IP. Everyone talk about that, but maybe you don't know what this, but I believe you heard about that, right? So for the IP protocol, that's the most important concept in this class. So I hope everyone should know that, right? Because after you learn this class, you don't know IP, what is IP, then that means this is not a very successful learning, or maybe I failed to let you know, right? But let's try to understand the IP clearly, okay? So this IP datagrams, as I mentioned, for each, you have learned the TCP template, right? You have learned the HTTP template, right? Format, right? And now the next is IP datagram format, right? So after I learned the first three chapters, at the list, I in my memory, I know the TCP format. What is the TCP format? If I don't remember every details, I know that the TCP includes something there, right? What is the congestion flow? What is the flow control, right? Something there. And for HTTP, right, you will have the different HTTP, the header data, header file, header fields, and some HTTP contents, right? And the different command for the HTTP, right? And here is the IP datagram format, similar, right? What is the format here? And okay, so we have the version number. For example, could be the version 4, and also could be the version 6, right? This is the IP version number, right? IP IP v4, IPv6, right? The version 6, version 4. But let's first focus. Sorry, let's first focus on the version 4 here, and the head length is just the head length, right? How many bytes here, and the length is the total datagrams length, and for example, maximum length could be the 64 k bytes, but typically it's only about 1k bytes or less, right? Every datagram. And because of the performance, right, or guarantee, we don't want to have a very long datagrams here. And the type of service, what does the type of service mean? So type of service is how the datagram should be used, such as the delay, reliability, minimum cost, the different service you want to put here, okay? And the TTL, I think you know the TTL from the previous sections. So this is the remaining time for live, right? So for example, I give a 1 day or 2 day, right? How much time you want to give for this datagram, right? And the upper layer is a TCP or UDP, right? Because when you send the packet, you need to indicate what is the upper layer, right? The upper layer is for example, TCP upper layer is HTTP, right? And this IP upper layer is TCP. You need to indicate that, right? And these two things are about the fragmentation, right? Just I mentioned, you need to do some fragment if it's when it's possible to accelerate the routing speed, right? And this two numbers to indicate that if you want to do the fragmented or not, whether the datagram is fragmented or not, right? For example, in the flags here, if it's 1, it indicates that this datagram can be fragmented, okay, or not, right? So you will have I think a 0 means can be fragmented, 1 means cannot be, okay. Uh, 0 is can, 1 is not. Okay, and fragment offset here means how you assemble the fragmented datagram, right? You need to indicate the offset, right? How many bytes you need to offset to assemble them together. And here's the header checksum. We mentioned that to report if there is any error or not. Okay, and the other two things are definitely obvious is source IP address and destination IP address. Okay, so this is IP data format. Um, Okay, I think I cover most of the important parts here, but no worry, we will go through some of them later. For example, what about the TTL, right? And the different types of service here and the fragmentation or reassembly here, right? But I think this is quite straightforward. You just give a offset number or the flags if it can be fragmented or divided or not, right? This is how much you want to offset to reassemble the datagrams here. Okay, and this is a timestamp record token. There's some options, we just ignore that. And the overhead of the IP datagrams means that what is overhead? Overhead means that besides the data you want to put here, the TCP, UDP information here, how much extra information or how many extra bytes you need to put here. For example, it's a 20 bytes of the IP and 20 bytes of the TCP equal to 40 bytes plus application layer overhead for TCP and IP. Right? You need to put some extra bytes. It's like encapsulate, right? So you just add some extra information here. Okay. So I think it's almost the time. Sorry, I'm a little bit faster today because I want to go to the, as I mentioned, go to the IP chapter. So if you have any detail you don't understand, you can, contact TA or me and or search some other video. I will post this video also to the my learn, right? So the I learn. Okay. Any question before we close today? Okay, so if you need more time for the assignment 3, you can please contact with me. Um, I I think most of you, I just quickly went through the assignment. I think most of you did a good job. Some of you may, face a challenge. For example, they are not very familiar with the Python. They are not familiar with the multi-thread programming. You can contact me. We can do some discussion, for example, because for the fairness, right? So I cannot give you no penalty, but maybe just several 5 to 10 points penalty, and then determine how much score you can get, right? And also considering a lot of the midterm last week, but just a case by case, okay, or determined by other situations from you, okay. So just send me an email or contact me, and I will involve TA, okay.
I have a question about the homework.
Mm-hmm.
I was just wondering mostly about the solution. So I remember that it required us to implement the multi-threaded server that would serve each client its own thread. Um, so I implemented that, but for some reason, sometimes specifically in multi-thread environment, basically every time I would say like the server accepts requests, and whether there's a new request, it will start a new thread and just accept the request and process it in that new thread that calls a function, basically calls a function, passes the
Mm-hmm.
argument, which is like the socket
Mm-hmm.
and the address. And so when I did that, sometimes once in a while it will some reason call, like for example from browser, if I try to access it from the browser, it will call a few threads instead of one. And for some reason one of them would say, for example, they couldn't find a file, or run into like IO error when I try to reach the file, and says it runs into IO error exception. Um, it kept doing that like once in a while, which would then result into the thread not processed properly.
Okay, so if you are you is your program fine with a no multi-thread version? You just a single thread version is working or not?
Yeah, yeah, single thread seems to be working fine. The multi-thread for some reason would keep sometimes running into IO error once in a while. Like it would be like hit or miss. You know, sometimes it works, sometimes it just doesn't. Just was kind of unreliable.
Okay, so I think there is some students give you the hint about that there is a separate get request for the multi-thread version. So because the browser look for the something default and yeah, I think many students yeah, I think give you the good answer. Uh, yeah, here. So anyway, I think, yeah, this is a good question. I suggest that we can have a separate time to discuss about this. And I think, yeah, if fine if you are not starting with a multi-thread version. If the single version mostly working, you should be good. And but yeah, multi-thread, if it's your code is working, that would be better, right? You can get the full credit, but we will consider, right? So some situations there, right? Um, okay, so let's talk about how great that with the TA together. But the general after yes, students, you can check their hints and see if they can their suggest can help you to solve this question. Okay, you can check there is some multi thread get request the browser need to look for. Okay.
Okay.
Mm, okay. So what would be expecting our report sign instruction on the website? Okay, that's a good question. So in the report in the future, I expect you to mention how make your program work, right? And what is the output from your program, screenshot or text description with a figure, something nice report, that would be great. Okay, and at least you should let TA know how to run your program. Okay, even it's very standard, it's better to mention how you make it work. Otherwise, different program can be running in the different configuration or different input argument, whatever, right? So I think that's a basic thing. You need to give a simple instruction how to make your program work and report the results with a screenshot or with some standard output, some text or something, right? Try to make it organized. Okay. Yeah. Okay. Thank you, everyone. See you on Wednesday. If you have any question, I think let's make an appointment. Okay. I think I may not be always there, but send me an email as I mentioned before the office hour. I will be there. Okay. Yeah. Thank you, everyone. Okay. Have a good day. Bye bye.